What's up, class? So, as you have noticed, it's almost October, and our first semester at Ateneo is about to come to an end. So, I hope that you are still, holding on and surviving this semester, and this all of it is new for all of us. And I hope that you're also taking care of your well-being apart from your academic duties. So, moving things forward, this will be lesson 7 of our EE2165, our DC circuits course. And in lesson 7, we will be talking about first order circuits. Now, in the previous lesson, or in lesson 6, we have encountered capacitors and inductors for the first time and somehow learned about how they operate, their basic operation and functions in a circuit. But in reality, capacitors and inductors operate with respect to time, or because capacitors and inductors are energy storage elements, and storage elements generally function with time. Like, for example, if you have your battery for your electronic devices or your smartphones, it will not stay in charge forever. There will come a time that these battery operated devices will cease to function because the stored energy is limited. And the same is true for capacitors and inductors. So we need to understand that the operation of capacitors and inductors should be analyzed on a time perspective, and thus this lesson will provide us with that sort of basic knowledge. So capacitors and inductors, as well as resistors, are the three most basic circuit elements that you can see in any circuit. But our analysis so far is just limited on the basic forms of circuits, like 1, 2, or 3 resistors, a capacitors, and an inductor. So we haven't moved to more complicated circuit elements yet. But um, please be mindful that these networks comprise the basic basic functional unit in any integrated circuits, which are composed of hundreds or thousands of the basic circuit forms that we have discussed so far. So have you ever wondered how our mobile phones, computers, and home appliances become automatic? It is because of these capacitors and inductors, storage devices. So, with in our analysis with respect to time, these elements, or these circuits with capacitors and inductors, can operate like a domino effect, in which once a circuit, or a basic unit of the circuit, becomes triggered, the rest of the circuit can also be triggered, which will prompt a particular action uh, on a particular time. So that's the importance of why we need to analyze circuits also from the perspective of time. So we have two main learning objectives for this lesson, for lesson 7, for first order circuits. First off is, number 1, we need to understand how circuits function with time, because in so far in our EE2165 course, we haven't conducted an analysis yet which involves time. So this will be the first time that we will encounter circuit analysis with a time element. And the second learning objective would be to help our understanding on how to design circuits, because as mentioned in the first item, um, circuits can be designed to function or prompt an action at a particular time, and depending on how long or how short you want your circuit to prompt an action, can be designed using the correct values of inductors and capacitors. So by adjusting the values of these circuit elements, we can therefore have some sort of idea on how time time-bounded circuit elements can function. So that's it. But this analysis will be brought to us by differential equations. So we are using differential equations for to obtain the formulas because of the element of time. As you have already learned from DE or from differential calculus, about the time rates or rate of change. And so inductors and capacitors also operate on a time rate perspective. That's why we are using differential equations. But rest assured that this use of differential equations in our lesson is not that difficult, so that you don't need to be daunted by the prospect of differential equations. And this also becomes another testament that mathematics and science and applied science goes hand in hand, and that mathematics do not intend to make our lives miserable, but rather make our approach to things much easier, much more organized. So this lesson will be composed of 4 topics. We have first off source-free RC circuit. The second would be source-free RL circuit. And then the third and fourth would be RC and RL circuits with a source, be it voltage or current source. So that's it. So at this time, let's discuss about the first topic, which is the source-free RC circuit. Now, we need to what you call this understand how a source-free circuit operates before moving on to a circuit with a source. So how can a circuit operate without a source? Remember that our capacitor is a storage element. So a source-free RC circuit is therefore not a dead circuit. This happens when the RC circuit is suddenly disconnected from the source, just enough that the capacitor has stored charge. So this stored energy is dissipated in the resistor over a period of time, which usually just lasts for a few seconds. And this dissipation of energy is simply an exponential decay of voltage VO, or the initial voltage. So again, why do we need to understand a source-free circuit? It is in order for us to understand what is like the natural response or the natural behavior of a circuit. So in the diagram, you can see that the circuit is comprised of one capacitor and one resistor. So the derivation of this formula, of the voltage formula, can be obtained using differential equations. So at this point, let us derive the formula for a source-free RC circuit, or a formula that will enable us to calculate the voltage with respect to time in a source-free RC circuit. Now, assuming that the capacitor is initially charged as I previous here, just enough when the capacitor has stored charge. So our capacitor is initially charged. So on that condition, the voltage at the start, when our time t is equal to 0, is given by this one, v at time equals 0, or VO, and this value is held constant. So on most cases, we always have a constant value of initial voltage that is being charged in the capacitor. So this time, applying KCL at the top node. As you can see, there is a node at the top. So the KCL will look like this: I sub C plus I sub R is equal to 0. And by definition, our IC, or our capacitor current, is given by C dV over dt, the derivative of voltage with respect to time, and our resistor current IR is equal to the Ohm's law, V over R. So substituting this will yield C dV dt plus V over R is equal to 0. Or dV, or just rearranging terms, dV over dt plus V over RC is equal to 0. So this is an indication, class, that we have arrived at our first order differential equation. So by regrouping the terms, just to regroup the terms, for the formula to be ready to be integrated, we will have dV over dt, no, dV over V is equal to negative dt over RC. So we can proceed rather with the integration, and integrating both sides will yield dV over V will become ln of V. So that's one of the types of integration formulas that you've encountered. Then equal to negative T over RC plus ln A, in which A in this case is our integration constant. So moving terms around, ln V minus ln A is equal to negative T over RC. So therefore we have ln V over A is equal to negative T over RC. Now to eliminate the ln, we take them to powers of E. So E ln V over A is equal to E on the power of T over RC. So we can therefore eliminate that one, and then we have the formula V over A is equal to E on the power of T over RC. Then continuing the formula over here, we have V over is equal to AE negative T over RC, or indicating that our voltage is operates on a function of time. Wait, where is that? Vt so to AE negative T over RC. Now, from initial conditions, our A is actually VO, or the initial voltage, which is the constant, and we will substitute that to our formula for Vt is equal to VO E negative T over RC. So this is now our formula. Don't worry, class, that the differential equation aspect of it has been provided to you already, and so when we go to our assessment or quizzes, you don't need to do the entire derivation thing all over again, because this is the formula that you will use, and that you will directly substitute the given in this formula. That is why we have it over here. This is our voltage formula. Vt is equal to V sub O e to the power of t over tau, where our tau, or time constant, is equal to RC, which is this one. So in case of having multiple resistors, we will only find the equivalent resistance R sub EQ by the concepts or strategies that we've learned from past lessons. And in order to find the current and power, you simply need to do the Ohm's law and have the power formula. So as easy as that. So this is our source-free RC circuit, and so to solve a source-free RC circuit requires only two things. Number one is the initial voltage V sub 0, or the voltage at the time at the time is equal to 0 across the capacitor, which is constant, or most of the time a given entity for the problem. And the second thing that we need to calculate is the time constant, the tau, which is equal to R times the value of the capacitor. So at this point, let us learn about what time constant is about. So why do we need to calculate the time constant, or what's the significance of the time constant? So time constant refers to the time required for the response to decay to a factor of 1 over E, or 36.8% of its initial value. So as indicated in this graph going down, this is what I meant when I said that the dissipation of energy is simply an exponential decay of voltage V sub O, or V sub 0. So because our source-free RC circuit has a limited reservoir of energy, this energy will be dissipated in just a matter of seconds, and that we need to, in order to understand the full cycle, we need to understand first the concept of time constant. So time constant indicates the speed in which the stored energy of the capacitor will be dissipated. So all of the stored energy will be dissipated after 5 time constants, regardless of the value of the tau. So time constant is actually the measure of how fast or how slow our the response time would become. So the smaller the time constant, the more rapidly the voltage decreases. That is, the faster the response. So if you are designing a circuit with for a faster response, or you want your circuit to respond faster, you will only adjust the value of the time constant by adjusting the values of the resistor R and the capacitor C, which will help us achieve a desired source-free RC circuit speed of response. So just I mentioned earlier from the start, that this lesson will help us understand how to design circuits, and this is one of the aspects in which we build on some sort of appreciation on how to design a circuit by adjusting the time constant, and therefore adjusting the speed of response by our circuit. So at this juncture, we will solve a sample problem using this formula, of course. So we are given with this problem in which we are meant to solve for Vt. So this Vt is actually the voltage across the capacitor. So we have conditions. Before proceeding to the source free aspect, the capacitor or the network still needs to be charged. So at the moments before the switch is opened at t is equal to 0, the entire circuit is connected to the source in order for the capacitor to store a charge. So we need to do a two-part calculation in order to solve the problem or in order to find the Vt. So wait. So the first part is when the switch is closed, the capacitor is an open circuit. So I need you to remember, guys, that in the previous lesson or in lesson 6 we learned that under DC conditions the capacitor is an open circuit. So this is basically a continuation or of that lesson, or this lesson builds up on that idea or concept. So since the capacitor is an open circuit, we will just have to redraw the diagram in order to understand it better. So you have 24 volts, then we have the 6 ohm resistor, then as an open circuit we only have this one, V sub C, and then we have another two resistors in parallel, which is 12 ohms and 4 ohms. So to solve the equivalent resistance, we have Req is equal to 12 times 4 by parallel addition of resistors, 12 times 4 over 12 plus 4, and that is equal to 3 ohms. Now by voltage division, Vc of t is equal to 24 volts, which is our main voltage source, times the resistor network concerned, which is 3 ohms over 3 ohms plus 6 ohms. So we have our Vc to be equal to 8 volts. Then the second part is since at TO, or since the time when t is equal to 0, the capacitor voltage does not diminish immediately. So in order to observe that what you call this reality, we have V sub C, which now becomes our V sub O is equal to 8 volts. So our V sub O class is a constant value since we have the circuit initially connected to a voltage source. When the switch is opened, at t is equal to 0, our circuit will be redrawn in this manner. So we have a capacitor which is valued at 1 over 6 farads, and then our Req, which we solved previously to be 3 ohms. So to calculate the time constant, we need to calculate the time constant first before proceeding to our Vt formula. So we have tau is equal to Rc, and our R in this case is 3 ohms, and C is 1 over 6 farads. That is equal to 0.5 seconds. So we have a unit of measure for our time constant to be seconds because we're talking about time. Therefore, our Vt is equal to Vo e to the power of t over Rc over 8 e negative t over 0.5, or our Vt in this case is equal to 8 e to the power of negative 2 t. So this is our final answer. Take note, class, that in the problem we did not specify at what voltage to calculate at a certain time, but rather we just need to solve for Vt. So we obtained the formula for Vt in this form, in which the variable t is left in the formula. So once we get this formula, we can calculate the value of the voltage at whatever time that we need to calculate it, but it usually diminishes or dissipates totally within a few seconds. So there you have it, class, our final answer. Our Vt is equal to 8 e to the power of negative 2t. So this time let's discuss about the source free RL circuit, which is our second topic. So like the source free RC circuits, inductors can also operate without a source, but only for a limited time. This happens when RL circuit is suddenly disconnected from the source just enough that the inductor has stored energy, so they operate uh, more or less same with the source-free RL circuits. Only that the dissipation of energy is simply an exponential decay of current I sub 0. So our current would eventually dissipate or die off in a matter of seconds. And this is because of the inherent characteristics of the inductor itself. So take a look at this diagram. This is a source-free RL circuit composed of only inductor and a resistor. And it can it can be in a different form, but for the purpose of this analysis, let's stick to this diagram. So how do we obtain the formula for IT, for the current formula? So let's go to the derivation of a source-free RL circuit. So this is the same diagram that we've seen just a while, and assuming that the inductor has an initial current right after disconnecting from the source, our current then is I when t is equal to 0, which is equal to I sub 0 and is therefore constant. So most of the time we will always have an initial value for our current. Now, applying KVL in this one loop at the loop yields only two voltages. We have voltage across the inductor VL plus voltage across the resistor VR equal to 0. By definition, VL is equal to L di over dt, or the derivative of current in terms of time with respect to time, and then VR is simply equal to current I times resistor R. So we will substitute that to our KVL equation. We have L di over dt plus I R is equal to 0, or rearranging the terms, di over dt plus I R sub R over L is equal to 0. So this is an indication of our first order differential equation. So rearranging the terms a little bit, we have di over dt is equal to negative I R over L, and then di, moving I to the other side of the equation, we have di over I is equal to negative RL dt. This is now ready to be integrated. Ready for integration. So di over I will become ln of I is equal to negative R times t all over L plus ln of I sub 0, or the integration constant. We will have ln of I minus minus ln of I sub O is equal to negative RT over L. We have ln I over I sub O is equal to negative RT over L. Then eliminating ln using powers of E, this constant, we have E ln over on the power of ln I over IO is equal to E to the power of RT over L. Continuing the solution over here, we have I over IO is equal to E negative RT over L. And then our I, or simply our I as a function of t, is equal to IO E on the power of RT over L. But our time constant tau is equal to L over R, and this therefore simplifies the form of the formula. So we have I of t is equal to IO E negative t over tau, or our time constant. So this is our current equation for our source-free RL circuit. So what you just need to do is substitute the given in this formula in order to obtain the equation of I as a function or current as a function of time. So that's how we obtain this equation. I of t is equal to I sub 0 e to the power of t over tau, in which our tau or our time constant is equal to L over R. Remember that our tau for the RC circuit is equal to R times C. Now in the RL circuit, our time constant tau is equal to inductor L divided by the value of the resistor R. So again, in case of multiple resistors, you just need to find the equivalent resistance. And to find the voltage and power, you simply need to do the Ohm's law and the power formula. So the same with source-free RC circuits. In order to solve for a source-free RL circuit requires two things. First is the initial voltage or the current at the starting time through the inductor, and of course the time constant. So again, the significance of the time constant is that the smaller the value of time constant of a circuit, the faster the rate of decay of the response will become, or the I of t curve, as you can see in this graph. The larger the time constant, the slower the decay of the response. At any rate, the response decays to less than 1% of initial value after 5 time constants or 5 tau. Adjusting the value of the time constant can be done by adjusting the values of R and L. So that's the same approach to how we can have some sort of idea on how to design a circuit, and this will help us achieve a desired source-free RL circuit speed of response. So you can lengthen or shorten the response time by adjusting the time constant, which is done consequently by adjusting the values of R and L. So at this time, let's solve for a sample problem. We have this one. We need to solve for the equation of current I as a function of t. The problem does not tell us what the value of current is at a particular time, so let's just leave the variable t at the in our final answer. So again, we have two parts. Just starting one. First part is when the switch is closed, the inductor is short-circuited. So we have learned from the previous lesson that under DC conditions, which is exactly still the same in this case, the inductor is a short circuit. So let us treat our circuit analysis with respect to that sort of reality. So when the inductor is short-circuited, this means that the 16 ohm resistor, which is the resistor adjacent to our inductor, will be discarded. So once an element is short-circuited, that element cannot have a bearing in the entire circuit anymore. So if we are to treat the inductor as a short circuit and the 16 ohm resistor to be discarded as well, we will just redraw the diagram like this. We have 40 volts, we have 2 ohms, we have 12 ohm resistor and our 4 ohm resistor. So we can solve for the equivalent resistance of this network. First, we have Req is equal to the parallel sum of 4 times 12 over 4 plus 12, and that is equal to 3 ohms. Quite familiar. Now, solving for the for the circuit current, for the current of this simplified circuit, we have I is equal to V over Req is equal to 40 volts over R. No, this is simply R. We have 3 ohms plus the existing 2 ohm resistor on top, and we have 8 amperes. By current division, we can obtain the initial value of IT, which is basically our I sub 0, the initial current. So IT or I sub 0 is equal to our main current 8 amperes times the adjacent resistance of this encircled network here, 12 ohms over 12 ohms plus 4 ohms. So that is to find the current across or current through the 4 ohm resistor. So our IO then, or I when T is equal to 0 is equal to 6 amperes. So that's an important part of our entire solution. So for the second part, we have when the switch is closed at T is equal to 0. So when the switch is closed, we can redraw. No, this is wrong. When the switch is opened, rather. So when the switch is opened, the 2 ohm resistor as well as the 40 volt voltage source will not have a bearing anymore, and so in order to understand that, we need to redraw the circuit again. We have 12 volts, obviously missing the voltage source this time. Then we have 4 ohms, then 16 ohm resistor, then of course our inductor, which is valued at 2 henries or 2H. We need to obtain the value of this resistor network again. So our Req, which is our encircled network, is a combination of series and parallel sum, series and parallel addition rather. So you have the resistors in series is 12 and 4 ohm resistors times its parallel resistor, which is 16 ohms, over the addition of these 3 resistors. Calculating that would yield 8 ohms, so that's our equivalent resistance. But before proceeding to the final approach of the solution, we need to calculate the time constant first. So our time constant, or tau, is equal to L over Req, which is equal to 2 henries over 8 ohms. So that is 0.25 seconds or 1/4. So therefore, this is our final step, is to solve for what the formula of IT will look like. We have IT is equal to I sub 0 e to the power of r t over L, or I sub o e to the power of negative t over tau. Then we have IO to be equal to 6 amperes, e negative t over our time constant is 0.25 seconds. Our IT therefore is equal to 6e negative 4t amperes. So that is our final answer. This is what the current formula looks like for our given circuit diagram. So no need for any sort of complex approach, class. This is actually made to be simplified for you, and you just need to remember or familiarize the formula in order to obtain this to obtain this equation. So this time we will move on to circuits with a source, and starting with RC circuits. Now, in reality, circuits often operate with a source. So it's not nearly possible that a circuit is just standalone, but we have those previous discussions about source-free circuits in just for us to understand how a circuit behaves intrinsically. So when the voltage source is suddenly applied, the RC circuit experiences sudden change in voltage. So unlike source free, where our voltage would just die down, in an RC circuit with a source, our circuit experiences voltage rise. So there's a difference in conditions between the moment where the RC circuit has no source and the moment where the RC circuit is suddenly connected to a source. So in our analysis with RC circuits with a source, we need to understand that there are two parts again. Two parts for our analysis, in which the part where the circuit responds naturally, and on the aspect where the circuit responds under the influence of an external voltage source. So as you can see in the diagram, we have the addition of a Vs, or the voltage source, and in this graph here, in the graph below, there are two voltages, VO and VS. VO is the one that is lower than Vs, which is at the top. So VO is the voltage of the RC circuit when the capacitor is initially charged. So remember VO in our source-free RC circuit. This is the voltage which is produced by the energy stored. What do you call that? Let me reword that. VO is the voltage brought about by the stored energy in the capacitor, across the capacitor rather. But in the addition of an external voltage source, we have Vs, and Vs is the final voltage of the RC circuit after the independent source has been applied. So it is the final voltage, or the steady state voltage, after a long time. So as you can see in the graph, Vs is the tangential to a horizontal line, because it approaches steady state, and by saying steady state, which it implies that our voltage does not change anymore with respect to time, so it flats up. So Vs will always be greater than VO because of the additional influence of the applied voltage source. So Vs is something that we cannot see in our analysis with source-free RC circuits. So again, this implies that the complete response to solve RC circuit with a source has two parts. So the first part is the natural response of the circuit without without the influence of the independent source. So the natural response that we are talking about is the intrinsic behavior of RC circuit as if it is source free. So the complete response is uh, comprised of natural response, and this time has the addition of the forced response, in which this is the response that is brought about by the independent source. So if in terms of voltage, in the perspective of voltage of the circuit, the natural response can be seen with the V sub 0, and the forced response can be appreciated with the V sub S. So I've also placed here the equivalence of the complete response. So we have complete response Vt is equal to Vn plus Vf, in which our Vn is our natural response in which our circuit is source free, and our Vf is the forced response, which is the response brought by the independent source. So this is just our formula A. So this is one of two ways in which we can see or we can appreciate what sort of response is going on in our RC circuit with a source. So a complete response can be viewed as an addition of, as a combination rather, of natural response and forced response. But alternatively, we have formula B. We can also view the complete response as the sum of the transient response and the steady state response. The transient response is the temporary response of the RC circuit as the voltage increases in the voltage curve graph over here. And the steady state response is the final or the permanent response of the RC circuit after a long time that the RC circuit has peaked its Vs curve. So the Vs, that voltage at the steady state part. So alternatively, we can analyze the RC circuit with a source by adding the transient response or the temporary part, the response that dies out over time. The response that is temporary and the steady state response, which is the permanent or the final response of our circuit. So I prefer to use the latter because that is where we can obtain these formulas from the first order differential equations, which I'm gonna do next. So the complete response is given by Vt, which is equal to V of t rather, which is equal to V sub t plus V sub ss, in which our V sub t is our transient response, which is the voltage curve in this case. The curve part is our transient response, and this is given by Vo minus Vs, quantity E to the power of t over tau, and our steady state response, which is our voltage peak, the Vs. So our steady state voltage or VSS is practically equal to our Vs in this graph. So that's the final voltage. It cannot go high or lower than that. It flats out. So these are your given formulas, and at this juncture perhaps we can derive the differentiation. We can derive rather the formula for our RC circuit with a source. So assuming again that the capacitor is initially charged initial charge before the source is applied, before the independent source is applied at t is equal to 0, we have the voltage at the start, or our V sub O, is constant. The same condition. Then applying KCL, at the top node, yields, we have I, the capacitor current I sub C, plus the resistor current I sub R is equal to 0. So by nodal analysis, and definition of capacitor voltage, we can substitute IC to be C, the derivative of voltage in terms of time with respect to time, plus our IR in this case is equal to V minus Vs all over R, and we equate that to 0. Then we just have to rearrange the terms. So this is the indication that we've achieved the first order differential equation. By regrouping the terms, so it becomes ready to be integrated. You have dV over V minus Vs is equal to negative dt over RC. So we will now integrate it, but this time we will have limits. We have the integration for the left side, we have VO, from VO to V of t. Then for the integration in terms of time, we have to start from 0 to an arbitrary value of t. So this integration will yield us with ln Vt minus Vs minus ln Vo minus Vs is equal to negative t over Rc plus 0, because that's our initial value. Or we can rearrange this a little bit. We have ln Vt minus Vs is equal to Vo minus Vs is equal to negative t over Rc. So again, we need to eliminate ln. We have to use e power of ln Vt minus Vs over Vo minus Vs is equal to e to the power of negative t over Rc. So that eliminates our ln on the left side of the equation. We have Vt minus Vs is equal to Vo minus Vs is equal to over VO over V minus VS rather is equal to E negative T over RC or E to the power of T over tau, which is our time constant. Our time constant being equal to R times C. Then we have Vt minus Vs is equal to VO minus Vs E to the power of T over tau. Then our Vt is equal to Vs plus VO minus Vs E to the power of negative T over tau. So this is now our final answer. This is the final formula rather. We haven't arrived with an answer yet. So we have two parts in this formula. This part over here is the transient response. And this part over here is our steady state response. So there you have it, the derivation of an RC circuit with a source. That is how we obtained this entire set of formula. Now in the case of multiple resistors, you just need to find the Req or the equivalent resistance, and to find the current you just need to apply Ohm's law, and to find the power you just need to apply the power formula. Now you need three things or three prerequisites in order to solve the RC circuit with a source. First off is the initial voltage V sub 0 across the capacitor, or the voltage at time when t is equal to 0. Second is the final voltage across the capacitor, or the final or permanent or the steady state voltage. And the third of course is the time constant tau, which is same with the source free RC circuit. So at this time, let us solve for a sample problem. So this problem requires us to solve for the complete response of V as a function of time. So the V that we are talking about here is the voltage across the capacitor. So there is only one capacitor here, but there are two voltage sources and three resistors. So we can solve this in two parts. The first part is when the switch is at position A, and then the second part is when the switch is at position B. So for switch at position A, we can immediately recognize that on position A we can neglect or discard the 4 kilo ohm and the 30 volts resistor circuit branch. So in order to clarify it, we need to redraw the diagram this way. We have 24 volts, the 3 kilo ohm resistor, then the 5 kilo ohm resistor, then our VC or the capacitor voltage, in which in this case again we need to remember that under DC conditions our capacitor is analyzed or assumed as an open circuit. So we have two resistors here, but our capacitor voltage VC is actually equal to the voltage across the 5 kilo ohm resistor. So in order to solve that, we need to do voltage division. So VC is equal to 24 volts, the main voltage source, times 5k, because that's the voltage that is the same with VC, over 5k plus 3k, and our VC is equal to 15 volts. And our VC is actually equal to our VO, or voltage at time is equal to 0, so we will just write again the 15 volts. This is because the capacitor voltage does not diminish or change immediately. So right before moving the switch to position B, the VO, or the V sub C, or the capacitor voltage is equal to 15 volts. So the second part is for switch at position B. We will redraw the circuit once again because the left side of the switch will not have a bearing for what the circuit will gonna look like. So we will redraw this time with the capacitor 0.5 millifarad. Then we have the 4 kilo ohm resistor, then the voltage source, which is equal to 30 volts. So from this simplified diagram, we can easily calculate for the time constant. We have value for R and C, so our tau, or time constant, is equal to RC times 4000 ohms times 0.5 millifarad. Our time constant therefore is equal to 2 seconds. So at steady state, so our steady state is defined as something that you can obtain after a long time, or after approximately 5 time constants the capacitor. What happens to the capacitor is that it then carries the voltage of the voltage source and becomes an open circuit. So when the switch is at position B, what happens after a long time is that our 0.5 millifarad capacitor will carry the same voltage as the 30 volt resistor. So that basically means that our Vs, or our steady state voltage, is equal to 30 volts. Now the complete response becomes Vt is equal to Vs plus Vo minus Vs e to the power of negative t over tau. We have 30 for our Vs plus our Vo. We find our Vo to be 15 volts. 15 minus 30 e to the power of negative t over 2. So our Vt, the complete response, therefore is equal to 30 minus 15 e to the power of negative 0.5 t, and that is our final answer in this case. So basically you're just substituting the values of the equation, values in the equation, and you will just leave the variable time t in the final answer unless the problem specifies to us to calculate the value of voltage at a particular time. Like for example, if we are required to calculate the value of voltage at t is equal to 4 seconds, then you will just basically substitute 4 seconds in the variable t in this formula, so you can obtain a constant value of voltage at a particular time. So that's it for a sample problem for RC circuits with a source. Now moving on to our final topic for this lesson is RL circuit with a source. So this topic borrows so much from its predecessor, which is RC circuit with a source. Just like its predecessor, the analysis of RL circuits with a source also has two parts, and perhaps the difference between them is the natural behavior of the inductor itself. So there same with RC circuits, there is a difference in condition between the moment where the RL circuit has no source and the moment where the RL circuit is suddenly connected to a source. So as you can see in the diagram, we have three elements in the circuit. We have the voltage source Vs, we have the resistor R, and of course our inductor L. But in the graph below, we can easily notice perhaps that the final or the steady state value of the current is less than its initial value. So they are quite opposite with that of the RC circuit with a source, because in the RC circuit case, the voltage source somehow supplements the voltage of the circuit, which increases the magnitude of the final voltage Vs, while in this case the final current is less than IO, or the initial current. So just a heads up, there are two currents, IO and Vs over R. So IO is the current of the RL circuit when the inductor is initially charged, that is on the moment before the circuit is connected to a source. Vs over R is still a current value, and this is the final current of the RL circuit after the source has been applied. So it is the final current, or the steady state current after a long time. Vs over R will always be less than I sub 0 because of the exponential current decay of the stored energy in the inductor. So the inherent exponential decay of current is something that we can expect naturally from the inductor. So it is by nature of the inductor. When the current curve has flattened to the Vs over R, the inductor acts as a short circuit and the voltage across it becomes 0. So that's the point of short circuit. The entire source voltage Vs appears in the resistor R, because when the inductor becomes a short circuit, the only element that consumes energy is resistor. That's why we use Vs over R to represent the final current in the RL circuit, just to make it clear. The complete response as the sum of the transient response and the steady state response is given in this formula. So we have transient response, again, is the temporary part, the part where the current graph experiences curve, and the steady state response is when the current flattens to Vs over R level. So the complete response is given by both transient transient and steady state response. So the derivation of this formula is highly similar to RC with the source and the source free RL. So this time I will not give you a derivation of the formula using first order differential equations anymore. So instead we will just directly substitute the formula to this given to what we have here. In the case of multiple resistors, we will just use the equivalent resistance Req, and when finding the voltage we will just use Ohm's law again and power formula when calculating for power. And same is true, we have three prerequisites in order to solve RL circuits with a source. The first one is the initial current through the inductor, the initial current I sub 0, then the final voltage Vs or the final current Vs over R through the inductor. So I'm sorry for this mistake. So Vs over R just slightly lower than IO, and of course our time constant tau, which is same with the source VRL circuit, which is L over R. So at this juncture, let us solve a sample problem. Now in this given problem, we aim to solve for the complete response of a current as a function of time, or IT. So there are two moments in this switching sequence. So the first moment is when the switch is still closed, and the second moment is when the switch has been opened at the start, or when t is equal to 0. So just to write it down, when the switch is closed, both resistors (5 and 10 ohms) are discarded. So both of these resistors are discarded because they are both in parallel to the switch, and when the switch is closed, both of these resistors are short-circuited. Also, the inductor under DC conditions acts like a short circuit as well. So that leaves us that our IO is therefore equal to 6 amperes, because there is no element that remains on the original diagram, and so our current, being the only current source, is equal to 6 amperes. So let us carry that as our initial current. Now for our second moment, when the switch is opened, both resistors, 5 and 10 ohm resistors, are functional. So redrawing the circuit once again, we have 5 ohms, then our inductor on the top, we have 1.5 henries, plus another resistor over here, 10 ohms, then our current source, which is equal to 6 amperes. So there is something that is familiar with a current source placed in parallel with our resistors. This can in fact become by source transformation will become a voltage source. So this diagram will become redrawing it again. We have 1.5 henries. Then the 10 ohm resistor becomes in series. The entire circuit rather becomes a series circuit. Then our voltage source is simply equal to current times resistor. So we have 6A times 10 ohms. We have 60 volts. So we obtained that by source transformation, which we have learned from the previous lesson. So since the 5 ohm and 10 ohm resistors are in series, we can add them in series. And that our Req in series is equal to 15 ohms. 15 ohms. Now our time constant tau is equal to L over Req. We have 1.5 henries over 15 ohms resistor. Then that is equal to 0.1 seconds. So after a long time, or approximately 5 time constants, our inductor carries the Vs over our current. So our steady state current ISS of t, or equal to Vs over R. Our Vs then is equal to 60 volts over Req, which is 15 ohms. We have our steady state current to be equal to 4 amperes. For the complete response, will look like just a simple substitution to the equation, to this equation right over here. We have I as a function of time is equal to Vs over R being the steady state, and then the transient response is equal to I0 minus Vs over R e to the power of negative t over time constant tau. Then we have Vs over R to be equal to 4 plus our I0 is equal to 6 amperes minus Vs over R again, which is equal to 4 multiplied by e negative t over 0.1 seconds. So our IT, our final formula for our current at any point in time, is equal to 4 plus 2 e negative 10t amperes. So that is our final answer. Unless the problem specifies to us to calculate the value of current at a particular time. So in that case, you just need to substitute the time on the t variable in the formula, and then you can obtain a current which is a constant at a particular time. So again, this is our final answer, and just as easy as that, we can calculate time calculate circuit analysis problems that involves time. So the differential equations are already derived for your convenience, so you don't need to do that anymore in our future endeavors. And hopefully I can send to you another assessment that is a combination of our lesson 6 and our lesson 7 before the week ends. So once again, we have just finished tackling our lesson 7, and I hope that if you have any questions, you can raise them on the Google Classroom. You can also chat me using the Hangouts or the Google Chat platform, or simply send me an email, whichever is more convenient to you. And if you find difficulty in viewing this video or recorded lecture, you can also pertain to our reference materials, and I will also send you a copy of the sample problem so that we can go back to them uh, at your convenient pace. So once again, thank you so much for listening, and I hope that you take care and yeah, stay strong.